When you go through a black hole, mathematically, no one's ever done this, of course, but mathematically, if you go through a black hole, you wind up on a parallel universe.
First of all, the black disk in the center is the event horizon, the point of no return.
Black holes are considered one of the most intriguing and interesting cosmic phenomena. They're cosmic vacuums that absorb everything, even light. Michio Kaku, a famous physicist, thinks we've solved the black hole mystery. Recent scientific discoveries have surprised us and promise to reveal these cosmic giants' deep secrets. Is a black hole a portal to other realities? Join us as we explore startling findings that may disclose black hole secrets. Black holes are cosmic riddles that puzzle us. They captivate us and challenge our comprehension with their mystique. In this mysterious region, time defies assumptions, confusing even the greatest minds. This raises the question of what a black hole is and why this apparently simple area is so powerful. Gravity pulls everything. For black holes, gravity is maximized. But let's explore this celestial show. Black holes form from the cores of dead stars. Gravity dominates when these remains reach 3 times the mass of our sun after a massive collision. A black hole forms when this immense gravitational force crushes everything. These strange cosmic phenomena have such high densities that even light is pulled in by their gravity. Astronomers agree that most spiral and elliptical galaxies have black holes in their centers. We divide black holes into 3 types to comprehend these cosmic occurrences. First, we have stellar mass black holes, the smallest, around 1 to 100 times the mass of our sun. Black holes form when huge stars collapse owing to gravity, typically resulting in supernova or stellar explosions. Conversely, supermassive black holes are heavyweight champs. These giants weigh millions or billions of times the sun. Scientists think they merge with other black holes and devour surrounding stars to become so large. The intermediate mass black holes are in the center. These black holes weigh 100,000 times the sun's mass and have been seen just a few times. Michio Kaku proposes that mergers and accretion between intermediate mass black holes generate supermassive black holes. Black holes bring up a new area in physics for scientists beyond helping us comprehend how stars move and galactic architecture. They're like unexplored land, encouraging researchers to discover the universe's secrets. Albert Einstein's theory of general relativity revealed a fascinating concept: how cosmic phenomena affect space and time. Gravity keeps everything from falling into the universe. Explore dark holes. This cosmic mystery is like the ultimate space mystery. Due of their massive material density, they have a powerful gravitational attraction like a space magnet. Their incredible strength questions and reshapes our knowledge of the universe's basic principles, captivating scientists. The singularity at the center of a black hole is the most mind-bending part. Scientists struggle to fathom the complexity and mysteries of these massive forces. According to Einstein's theory, everything dragged into a black hole disappears altogether. Another major hypothesis, quantum mechanics, disagrees. It contradicts the belief that such an event cannot happen. Thus, black holes are a battlefield for these 2 major ideas, forcing scientists to reconcile and integrate them. Many think of black holes as space holes, but that's inaccurate. Consider them super intense cosmic magnets with stronger gravitational pulls than Earth's. Earth's gravity keeps us grounded when we jump. However, black holes' gravitational pull is much greater than Earth's, attracting things with unprecedented intensity. Black holes are named for their mysterious lack of a surface to stop their descent, giving the impression of plunging into an infinite abyss. They form when a massive star collapses, compressing an astronomical amount of material into a tiny space. Imagine compressing a star into a tiny dot. When so much stuff is crammed into a small area, gravity is severe. It follows that bulk increases gravity. Mass determines Earth's gravitational force, which grounds us. Compare Earth's gravitational pull to the Moon's, and astronauts look lighter. Why? The Moon's size reduces its gravitational force, making its surface seem lighter than Earth's. Black hole compressibility is intriguing and perplexing. It's amazing that a star like our sun can collapse, creating a black hole the size of a small city. The massive density caused by this change is hard to comprehend. A small city covers around 10 kilometers, but the Sun is 1.4 million kilometers across. This volume reduction emphasizes the amazing transformation from a star to a black hole. This highlights that calling them holes owing to their gravitational influence doesn't properly describe them. If black holes aren't empty voids, what are they? Technically, black holes are spherical entities with a singularity at their center and an event horizon. A point of essentially infinite density without volume, the singularity exerts a powerful gravitational force that characterizes black holes and molds their distinctive properties. The singularity at the core of a black hole is very tiny and dense. Imagine standing at Earth's North Pole. The northern hemisphere has more gravity than the southern, demonstrating the inverse connection between gravity and distance. This dynamic interplay with Earth's gravitational pull shows that forces vary. Gravitational pull is stronger in nearby areas. However, compressing Earth's bulk would increase gravity. The density varies, but the mass stays the same. Denser signifies more concentrated. Mass increases gravitational pull. Understanding how black holes and gravity interact shows their fascinating nature, challenging our understanding of space-time and the physical cosmos. The fascination of black holes drives substantial study in this sector. Michio Kaku, a renowned theoretical physicist, has spent decades developing the theory of everything. One promising hypothesis in this field is superstring theory. This hypothesis proposes that subatomic particles are tiny vibrating strings to unite gravity and radiation. It envisions the cosmos as a symphony of these strings, like violin strings vibrating in various pitches. Many natural particles align with superstring vibrations. Superstring theory's capacity to warp spacetime creates black holes, wormholes, and other fascinating Einstein equation solutions. This theoretical framework reconciles Einstein's gravitational theory with quantum theory and illuminates many perplexing natural processes as these strings travel through time. This theory's 10 spacetime dimensions are intriguing. This sharp contrast to our common understanding of 3 spatial and 1 temporal dimensions is confusing. These additional dimensions imagine a 2-dimensional pond with fish that only see length and breadth. Height is impossible. Fish see ripples as rains shake the pond's surface, indicating a 3rd dimension. These extra spacetime dimensions cannot be immediately seen, according to scientists. Instead, superstring theory's string vibrations produce energy waves that travel these unseen dimensions, affecting our reality. Superstring theory might explain all observable particles and forces, including gravity, by describing these waves as particles with mass and charge. These additional dimensions needed by superstring theory are very small, which presents a major issue. Our labs can only measure length, breadth, depth, and time. Thus, direct investigation is still impossible. In movies, the event horizon is a murky circular border in space that represents a black hole. An important barrier, called the point of no return, encircles the center core. Any object that crosses this border is immediately pulled into the center with no escape. The event horizon seems like a substantial boundary, although it has no substance or contents. Understanding that black holes are mostly empty is crucial. Singularity in the center holds all collected matter, while surrounding space is essentially vacuum, creating an appearance of deep darkness. Material and energy entering the black hole merge with the center singularity nearly instantly. The gravitational pull of black holes is enormous. Black holes cannot be seen because their power is so great that even light cannot pass through. Thus, scientists must use big radio telescopes and gravitational wave detectors to indirectly detect and investigate these mysterious cosmic events. Albert Einstein's 1915 theory changed our understanding of how moving things impact spacetime. This remarkable revelation united space and time. Imagine disruptions on a peaceful pond. In 2025, a century later, the Laser Interferometer Gravitational Wave Observatory made a major discovery. First ever gravitational wave observation by scientists. This amazing feat was achieved 1.3 billion years ago when two black holes collided. Black holes attract and superheat gas, dust, and stars, making their existence felt in the sky. Thermal traces indicate radiation from these components as they approach the black hole. The Event Horizon Telescope, a network of 8 terrestrial radio telescopes intended to photograph black holes, reached a milestone in April 2019. The first black hole shadow picture was captured. The black hole in the Messier 887 galaxy, a major component of the Virgo galaxy cluster, was the focus of this landmark photograph. The picture shows a bright ring around a 55 million light-year away black hole with a mass 62 billion times that of our Sun. The bright halo is the tremendous thermal emissions from the whirling hot plasma around the event horizon, the black hole's furthest edge before it collapses under its gravitational pull. Theories of black hole travel. Imagine a human being swallowed by a black hole. It would have dire repercussions. No matter the black hole categorization, the prognosis is poor. A person that spontaneously enters a stellar mass black hole will undergo spaghettification, a terrible bodily metamorphosis. Despite its fanciful moniker, this occurrence is not funny. The incredible gravitational attraction of a black hole would compress and stretch the person, creating a spaghetti-like shape. Entering a supermassive black hole is less disastrous than other options. Let us examine if, for the pursuit of scientific curiosity, or as a great leap for mankind, the case of a person deciding to fall into Sagittarius A, a supermassive black hole positioned at the heart of the Milky Way. This celestial phenomenon, first detected by Bruce Ballack and Robert L. Brown in 1974 and named in 1982, has a calculated 44 million kilometer diameter and 4.31 million times the mass of our Sun. Sagittarius. Exploration starts when a person passes the event horizon, a final frontier. Travelers can see their surroundings within this border, but outsiders cannot. External observers cannot see the person because internal light is captured and deflected inside. Despite the high gravitational pull within such massive black holes, the stretching effect is gentler, limiting the chance of spaghetti-like strands. Black holes' extreme nature makes direct observation and investigation impossible. Hence, these situations are speculative. However, black holes continue to fascinate scientists, helping us grasp the universe's complex mechanics. Escape from a black hole is difficult or impossible. However, white holes offer hope. White holes eject stuff, whereas black holes take it in. Thankfully, wormholes link black and white holes, albeit their nature is unknown. Although it would take billions of years, these wormholes may connect black holes to white holes. This notion must be acknowledged as theoretically explorable and refined. Kaku advises tempering expectations and avoiding irresponsible activities based on this notion. White holes and wormholes are intriguing and promising for interplanetary travel, but they are theoretical and need more research. Defying gravity in a black hole is a fascinating world to explore. Despite its gravitational trapping, this setting allows experimental research to further human knowledge. These efforts may question the idea that stuff eventually collapses into a black hole. Planck stars, a loop quantum gravity theory, are an interesting option. Loop quantum gravity is speculative science, hence it must be acknowledged. Its main goal is to provide a quantum framework to explain gravity. This approach quantizes space-time into discrete, limited bits. They seem to move macroscopically due to their exceedingly small size. Space-time granularity improves our comprehension of the universe in two ways. First, it provides a coherent quantum mechanics explanation for gravity integration. Second, it prevents black hole-centered gravitational singularities. Space-time's discreteness resists matter's collapse into a dying star due to gravity. This resistance limits matter's compression, preventing it from shrinking below the Planck length, 1.68*10 to the power of minus 35 meters. Every object that enters a black hole is crushed, but not reduced to minuscule size. Resistance stops compression, halting or reversing the collapse, which is more like a stoppage than an explosion. This suggests that black holes are fleeting and finite. However, from the outside universe, black holes die over billions or trillions of years due to tremendous time dilation. This temporal dilation reveals black holes' vast time spans and cosmic dynamics. Gravastars are a proactive approach to singularities that avoids quantum gravity theories. Astronomy sometimes uses such naming practices, despite seeming out of place. However, distinguishing a black hole from a gravastar is vital. The latter has dark energy, not a singularity. Dark energy, which permeates space and time, creates an expanding force. Even though it seems like science fiction, dark energy exists. Dark energy accelerates the cosmic expansion of our cosmos. Matter rushes into gravastars, but thick core dark energy prevents penetration beyond the surface. This contrasts with black holes, which have an event horizon from which nothing, not even light, can escape. Recent gravitational wave detector data by LIGO and Virgo during black hole mergers throw doubt on gravastars. Gravastar mergers emit signals that differ from black hole mergers, causing ambiguity. These detectors keep collecting data, casting doubt on gravastars. It's crucial to note that gravastars aren't technically banned in our reality. Their theoretical base is, however, unstable and under review. Scientific knowledge and fresh observational evidence are crucial to determining the veracity of these theoretical constructions in our cosmic reality. An amazing finding about black holes was discovered lately. A newly discovered black hole devoured a star that came too near. A tiny galaxy a million light-years distant had a tidal disruption event. The TDE shined brighter than any other star in that galaxy after emitting a strong blast of energy. This has given scientists a rare chance to study black holes and galaxies. This discovery also introduces a new intermediate black hole for investigation, improving our understanding of their diameters. This cosmic evolution is intriguing and promising to improve our understanding. Rings, singularities, and wormholes are intriguing topics. The singularity landscape goes beyond Planck stars and gravitationally collapsed stars. A new knowledge of black holes has led researchers to reject the idea of a single point of infinite density. This alternate view comes from understanding non-rotating, uncharged black holes. However, true black holes, particularly ones with angular momentum, behave intriguingly. Einstein's general theory of relativity predicts that a spinning black hole twists the singularity into a ring. Transitioning via this ring singularity may lead to a wormhole and emerging through a white hole, revealing a new and exciting cosmic realm. Due to their fast spin, revolving black holes are unstable, creating problems within. This instability creates centrifugal forces that push rather than pull, like anti-gravity. An inner horizon forms inside the black hole. In this location, enormous gravitational forces pull external radiation toward the singularity. Ironically, centrifugal forces cause radiation to have anti-gravity effects near the ring singularity. The inner horizon is a crucial border. Any encounter with it would expose a person to a blast of radiation with boundless energy that encapsulates the universe's history in a moment. This paradoxical interaction between gravity, radiation, and the ring singularity in spinning black holes offers a fascinating way to study the universe's deepest secrets. Using black hole collisions to refine models, an inner horizon is the first step in black hole development. However, whirling black holes test our mathematical frameworks, indicating unexplored occurrences. The discovery of gravitational waves has given us a rare view into these cosmic giants' mysterious innards. This latest scientific study will help us understand the catastrophic events that occur when these cosmic entities clash, a rare and significant occurrence. Scientists discovered gravitational waves in 2015. Complex and massive equipment were used to measure space-time disruptions following black hole encounters. Similar to the waves created by agitating a sealed container, such collisions ricochet across the universe, revealing its contents via sound analysis. These gravitational wave disruptions from two merging black holes provide vital scientific data. Scientists have used these observations to update their models of astronomical occurrences, allowing them to better understand their internal dynamics. This data also enables for a thorough test of Einstein's general relativity theory in severe cosmic conditions. Scientific models' predictive power came from linear interactions until recently. These models work, but they can't capture complex systems' various behaviors. However, non-linear interaction research offers a compelling possibility to improve these models by up to 10%. In the future, this development might let scientists detect and analyze colliding black holes more accurately and confidently. In our attempt to comprehend the cosmos, understanding non-linear interactions is a major advance. New insights into gravitational wave detection methods bring us closer to the next frontier of research. This development might improve our knowledge of gravity and reveal the amazing cosmic events. Our understanding of the universe grows, allowing us to explore its basic nature. Let's discuss tidal disturbance. Since 2020, the epidemic has halted LIGO, which discovered gravitational waves. However, impending system reactivations provide promise for improved black hole detection and investigation. A University of Michigan research led by Enrico Rinaldi explores the intriguing idea that black holes may be like holograms. Please note that this comparison does not depict black holes as science fiction. Instead, it uses holography to study the complex interaction between a black hole's core and outside. This study relies on holographic duality, which mathematically equates gravity and particle theories. Particle theory is in the second dimension, whereas gravity theory is in the third. Both dimensions are necessary to understand black hole dynamics. The Young supernova experiment first saw the tidal disruption event flare in 2020. This specialist astronomy survey was created to detect transitory cosmic events like supernova explosions. The early discovery of a black hole swallowing a neighboring star sparked a worldwide collaboration. This revolutionary project was led by experts from the University of California, Santa Cruz, and the Niels Bohr Institute, including astronomer Charlotte Angus. This study team accurately measured the black hole's mass. The accuracy puts the black hole's mass between 100,000 to 1 million times the Sun's. Before this finding, tidal disruption events were mostly used to estimate enormous supermassive black hole masses. This is the first time TDEs have revealed the masses of intermediate black holes, especially smaller to mid-sized ones. The rapid flare's discovery sets the standard for mid-sized black hole mass estimations. Capturing the mid-sized black hole consuming a companion star revealed previously unknown information. These black holes' flares provide insights on intermediate black holes, which might possibly make up most black holes in galaxies' cores. Scientists believe that supermassive black holes bigger than our Sun emerged from smaller intermediate black holes in the early cosmos. These intermediate black holes presumably lived in smaller galaxies and grew when they collided or were devoured by bigger ones. Most galaxies have huge supermassive black holes formed by this cyclical process. The presence of intermediate black holes in all tiny galaxies is a fascinating astrophysics subject. Black holes are only seen when actively eating matter or upsetting celestial objects, making them difficult to observe. Intermediate black holes in smaller galaxy systems are difficult to find due to their light-capturing properties. Exploring intermediate black holes is a major step in understanding galaxy development and composition. Unlocking these cosmic entities' secrets will illuminate the complex processes that have molded the universe's structure and behavior across cosmic time. Thank you for watching, and see you next time.